Welcome everyone. In this video I'm going to continue the experiments with strain gauges. So in the previous video I made this bar with this strain gauge in the middle of it, and what I did, I basically showed you how to install this strain gauge by using some adhesives, and I also showed you how to solder these wires to the tabs on the strain gauge, and then I did some experiments. So basically what happens here is that whenever I bend this bar in one or the other direction, then the grid, or more precisely the wires inside that grid, which is in the strain gauge, will be elongated or compressed. Therefore their resistance, or the grid's resistance, will change, and this can be measured. So I can actually demonstrate this resistance change, and based on that I can show you what's the problem with this thing. So now, let's say this is at zero deformation, and you can see that the resistance of this is very close to the nominal resistance of a strain gauge, which is 350 ohms. So now I pick this bar up and I bend it towards the camera. So that's a tensile force applied on the strain gauge, and you can see that the resistance of the strain gauge increased by roughly 1 ohm. So now I release it, and now I bend it so it will experience compression, and you can see that the resistance dropped by 1 ohm roughly. So this is our first problem, that the change upon the deformation of the strain gauge is very small. It's just 1 ohm. And the other problem is that this is resistance. And in electronics, we usually don't measure resistance because that's not so easy, or more precisely, it's not practical to measure resistance. So instead of that, we don't directly measure resistance. We somehow translate the resistance change into voltage change. And for example, that is done by this circuit, which I showed you in some of my previous videos where I was talking about strain gauges. And actually I use this thing in one of my data logger, which is a 4-channel data logger for strain gauges. So what you see here is a complete circuit, and it has a strain gauge here, and then this strain gauge goes into this PCB, which consists of two main, let's say, parts, and one part is Wheatstone bridge. So that Wheatstone bridge consists of 4 resistors, and one resistor out of these 4 resistors is the strain gauge. And then the output voltage of that Wheatstone bridge is going into this op amp here, and then we amplify that very small voltage change, and that amplified voltage change will appear on this output. And this is basically just powered by 5 volts. So then that 5 volt will operate the operation amplifier and also give the voltage to the Wheatstone bridge. And then there is a potmeter here, and that is just to shift the voltage, the output voltage of the operational amplifier. So you can put it to 0 or put it to 2.5 volts or something, and based on that, whenever you change the let's say strain state of the strain gauge, you will shift the resistance, you will shift the output voltage here on this pin according to the level which you set with this potentiometer. But my problem with this circuit is that I don't feel that I have all the controls over the parameters. And also I have this guy here, which I introduced you several times. So this is an AD converter, an ADS1256, and a STM32 microcontroller embedded in the same PCB. And what is good about this circuit is not only that it is a very nice compact circuit, but the ADS1256 has a built-in amplifier, and basically that's a PGA, Programmable Gain Amplifier. So you can change the voltage level of the input, and therefore you divide that voltage level with the 24-bit resolution. So you are not necessarily forced to use the chip at 5 volts, but you can divide it by 2 all the time. So you can go down to 1.25 volts or 600 something millivolts and so on and so on. So you can have very small voltages. So what I thought is that instead of using this and connecting this to this, I directly use this with a Wheatstone bridge. So what I built here is basically that. So we have a strain gauge here, which is one resistor out of the 4 resistors in the Wheatstone bridge. And then we have the 3 other 350 ohm resistors. So what we do here on the other side of this breadboard is just we give a very precise voltage to this Wheatstone bridge. So this is an LM317 voltage regulator with a very basic circuit. So it consists of 2 resistors, one fixed resistor and a potentiometer to precisely change the output voltage, and 3 capacitors. And basically that's all. So what we have here is a power supply, a Wheatstone bridge, and then we measure the output of the Wheatstone bridge. So now I replace this strain gauge with this other strain gauge, which is attached to the bar, and we measure how much voltage we can expect from the output. So basically everything is connected. So once again, I have an external power supply. I set it to 12 volts. 12 volts are coming in, and then the output of the voltage regulator circuit is here on the blue wires, and then it goes to the plus and minus side, or positive and ground side of the Wheatstone bridge, and then we get the output voltage of the Wheatstone bridge in the middle of the 2 voltage dividers on the 2 sides. So that's what we measure here. So now I turn on the power supply, and basically nothing happened. The voltage is really low, so I just change this. So we have 0.78 millivolts. So this is 776 microvolts. So what happens if all the components, all the 4 resistors have the exact same value inside the Wheatstone bridge, then the output voltage should be 0. But they slightly differ, so therefore the output voltage is not exactly 0, but it's very close to 0. But now I gently touch this thing, or even I just find something heavy. Let's say I put a battery on this bar, and we should see if something happens. So I put a very slight weight, I don't know, maybe 50 grams on this bar, and since it is sitting on the wires, then this can bend, and you can see that this deformation can be noticed. But you can see that this was basically 100, not even 100, it was more like 40 microvolts of change. 40 microvolts. So I remove this and you can see the change. So now it's 0.81 and now 0.77. So this is a very, very small change. So now if I bend it more significantly, you can see that we can even reach 1.2 millivolts or even more. So we can double or triple the numbers, and I'm still within the elastic deformation region of this bar. So that's nice, because that also means that we are within the limits of the strain gauge, because the strain gauge can measure roughly up to 2% elongation, and that is roughly the limit also for the elastic to plastic deformation. And now you can see that. So it works the same, but you can see that the change is in the microvolt, few tenths of microvolts change. So this is a huge issue, and this is what we will treat, or try to treat, with this guy here. So now when I continue this experiment, what I will do, I move this to my computer. I will power this with a 12-volt power supply, but then I connect the output, so these two things, connect the output of the Wheatstone bridge directly to this 24-bit AD converter. And then I will try to play with the PGA values and see how good readings I can get from the strain gauge. Because basically this is the problem here, that you could see that the voltage change was just a few tenths of microvolts, and that's why we need the op-amp here. But I think that we introduce some noise by having an op-amp here and then connecting this thing to this thing. And basically you can get rid of 90% of this circuitry by eliminating all the op-amp part and just keeping the resistors, which is here. And we have a very stable voltage regulator here. And that's all. So I will use this kind of circuit and directly connect it to this ADS1256. So in the continuation of this experiment, we will go to my computer and I will show you some numbers, and we will see what happens if we try to do everything from basically scratch. So we are at the computer and you are looking at my software right here, and you could see this in the previous video when I was playing with the strain gauge. So the circuit is the same. So we have the LM317 based voltage regulator, which provides the voltage to the Wheatstone bridge. And then one of the element in the Wheatstone bridge is a strain gauge. And that strain gauge is attached to this aluminum bar. And now the aluminum bar is in front of me and it is supported at the two ends. So if I push the middle of it, or if I place something on this, then the aluminum bar can bend and we can see how everything changes. And of course we have the ADS1256, which I showed you, connected to the computer. So the computer will receive the data and visualize it here. And I am also using a multimeter just to check my things. So if I'm looking at the multimeter now, I can read 60.77 millivolts on the output of the Wheatstone bridge. And this is the unloaded case for the strain gauge. So let's connect and let's see what happens. So basically we just select the COM port and we connect. And now I did something. So previously this part was full of buttons, and I want to rearrange the whole software and make it better. So now we can change all the acquisition parameters here, as you can see. So sampling rate, the refresh rate of the screen here, the PGA value, which we will have to change, and so on and so on. So now we just start with this and we will see what happens. But basically what happens now, I open the new form by clicking this button here, and that new form is this guy here. And when I selected these values, or even if I haven't, I have to click this button, and this will pass these parameters to the previous window, the main window, and that will send out the things to the Arduino. I did not want two different windows to communicate with the Arduino, so I think this is a better solution. But now we are connected to the Arduino. We have some initial parameters, so we select the strain gauge, and we are only caring about this thing here. And I haven't made the conversion yet, so we will see the raw data here, where we have the zeros, and we will see the voltage here, where we have the text labeled 10. So now everything is good to go. So I press start. And now we see 60.62, 67, all the time different values. But basically now, as I started everything and the circuits are running, the multimeter shows 60.54, and with the same sign, so it's a negative 60.56 millivolts, and you can see that it's basically 100 millivolts difference between the multimeter and the ADS1256. So that's pretty nice. And now you can see that basically this line is flat and it is not changing. So I put something on this beam and we will see if we get different values. So now I put something on it. And you can see it here that there was a gentle increase in the value. And now actually the strain gauge is compressed. And you see that now we read 40 something instead of 60 something. So what we see immediately is that the change in the voltage is in the microvolts region. So that's not so good for us because it's a very small, tiny voltage. So now I remove the weight from the beam or from this bar. And we went back to the, let's say, 60 something region. So it is a noticeable change, but it's still small. So now I press down the bar a bit more stronger. And now you can see that we changed digits also here. So we have a more noticeable change, and I released it now. So this is very, very small change. What I can do, I can stop the measurement and I can change the PGA. So as you can see, what happens with the PGA is that if you increase the value, then you restrict the resolution in between these values. So now we have -5 to +5 volts, so 10 volts range, and that is divided into 2 to the 23rd power equal parts. But we can do the same division with half of the region or half of the domain. So we start at -2.5 and go only up to +2.5. So instead of 10, we now have 5 volts region to cover with the same amount of resolution. So you can see that this will allow us to get finer and finer differences between two numbers. So if we have a perfect system, so we don't have noise and fluctuations and stuff like that, we can drastically increase our sensitivity for these small, tiny changes. So let's go for, I don't know, 156 millivolts, because we are, almost 3 times less. So I just send the parameters. So now the AD converter received these parameters, and I just restart the measurement. And of course now we have somewhat different voltage because we changed the amplifier, and also the multimeter now reads -61.36, and now here we have 39, 38, 40, 38, so in that region. And you can see that the raw data is also fluctuating just a little bit. I mean, this is a huge number, but only just these digits are changing. So now I press this down again. And you can see that it changed. Now I release it and it changed again. And of course this doesn't seem too noticeable because the scale is very large as compared to the fluctuations, but here I just want to show you that it works. And now I'm feeding the Wheatstone bridge with 5 volts only. So one thing that you can do in order to increase the output voltage of your Wheatstone bridge is you have to increase the input voltage of your Wheatstone bridge. But you have to keep in mind that if you increase the voltage, then higher current will flow through your device. And by device, I mean the resistors. And they might not like too high current. So I would avoid that. And I think it's safer, let's say, to keep the voltage low let's say something 5 to 10 volts, and instead of that we should go for increased sensitivity. And that increased sensitivity can be realized with this ADS1256, for example. So I think that this will work. I can get rid of that Wheatstone bridge plus op-amp circuit, and instead of that I can let's say create my own voltage regulator plus Wheatstone bridge circuit, and that will provide me a nice stable output voltage on the Wheatstone bridge, and I can measure that stable voltage, or hopefully stable voltage, and account for all kind of things. And the other advantage of my customized circuit is that I can replace the resistors, so I can make a half bridge or a full bridge, so I can add 1 or even 3 more different strain gauges, and that will allow me to compensate for temperature change, for example, and other things. So that can increase our, let's say, flexibility in measurement. So I think this was all for now. I just wanted to show you that I can capture these tiny changes more or less precisely. Of course, I have to do something with these small changes, but I will see what can I do, because if you remember from a few minutes ago, the breadboard is a huge chaos. So I guess a lot of noise is being captured by those cables and everything, because they can act as antennas. So I will put everything in a PCB and decrease the amount and length of wires, of course. Maybe add some capacitors to filter the noise where it is possible or where it is necessary, and then I will continue my journey with this kind of measurement, because I think that amplifier is not necessarily good. We can do it with the built-in amplifier of the ADS1256. It already has the amplifier, so why not use it? And why should we go for something which can potentially add additional noise to our very delicate measurement? So basically this was the video. It was more like an update and some presentation of proof of concept. And in the next video I will hopefully show you some real numbers regarding stress and strain, and we will see if we can really use those numbers in, let's say, real experiments or not. So I hope you learned something. If you have some questions or have some other ideas or something, please let me know in the comments. I am really happy to receive some feedback. And don't forget to visit my website, curiousscientist.tech. It has some extra information usually, and you can find all my articles and stuff there, so it might worth a visit. And see you in the next video.